Hey kids, Smath here. Welcome to chapter 18. 18 has three different topics in this for us. It has reaction rates, equilibrium, and thermodynamics. Now, these are generally considered the advanced topics for Chemistry 1. We're going to break each one of these up individually. I've got a couple of different. I'm going old school with you now. I've broken out a PowerPoint to try to get as much information as I can to you as simply as I can, and then I'll make some supplemental videos for the problems and be able to use the pad for that. So what are reaction rates exactly? Well, rates are basically that. It's a speed. Rate is how fast a reaction is going to occur. How fast, how slow. When we think about fast, we think about things like elephant toothpaste. We mix two things together, boom, it flows over. It happens immediately. Other things, we take a piece of iron, we set it out in the yard, we wait for it to oxidize, and this could take days, weeks, months, years. This could take a long time. So rates are just how fast. When we think about the rate, we're going to talk about the speed of the concentration. And so the concentration is going to be measured in molarity per second, okay? Molarity per second here, or moles per liter second that we're looking for. And so now I've got my pointer, there's my moles per liter second, or molarity per second. Now within this, we're going to have something called spontaneity that's also going to come into play, whether things happen by themselves or not. This is delta G. That spontaneity is, will it occur without us doing anything to it? It might, but it's going to take a long time. Here's the way to think about that is if we took some gasoline and waited for that gasoline to turn into CO2 and H2O, like a combustion reaction, that gasoline will combine with oxygen. Now that'll happen really quickly if we ignite that or put some sort of heat to it. If not, if we just take that gasoline and let it set out and sit in nature, it's going to happen. It's just going to take an awfully long time. So whether something will occur spontaneously lies independently of the reaction rate. Now, how do rates happen? Why do rates happen? Well, it's all based on this thing called collision theory. Collision theory is basically that for reactions to occur, things have to collide. There have to be collisions into it. Atoms, ions, molecules, they react when they collide. Now they have to collide in the proper manner. They have to have the right energy. They have to have the right orientation. The way I think of this, maybe inappropriately, is we have a car crash that's going to happen. This is a demolition derby, and we want both those cars to be disabled and knocked out of the race. They have to hit with the proper speed and the proper orientation, angle of attack. It also states that molecules can decompose if we put energy into them. And so here's a nice molecule. We put energy into that and it breaks apart. So those can happen. That's called collision theory. Now, for both of those things to happen, we have to have this thing called activation energy. And activation energy is merely the energy it takes to start a chemical reaction. And so this graph I have down here is called a reaction coordinate. And in a reaction coordinate, basically it is time on the X and energy on the Y, and as the reaction proceeds. And so we start with our reactants, and those reactants will go to products. But to get to those products, it has to have some energy put into it. That energy that's put into it is called the activation energy, E sub A, energy of activation. Now, the reactants gain that energy, they proceed and they turn into products. What happens is the difference in energy between the reactants and the products, that's how much heat is given off in the reaction. We just finished thermodynamics. Q, heat, enthalpy, heat, all right? That's the enthalpy of this reaction, the delta H of this reaction. Now, collision theory, we also have particles that have just enough energy. They're going to create this thing that's called an activated complex. Now, we will never see an activated complex. We'll never write an activated complex. It's not a stable orientation. It's very unstable. It's very high energy. Imagine this is back to the demolition derby where our cars are all zooming around and they're all colliding and they go through the figure eight. All those cars collide, and then some of them take off again. Well, that part where all those cars are collided and stuck together for just a split second, that's the activated complex. And at that point, the reaction can either proceed towards products or it can proceed backwards and go towards. Sometimes this is also called a transition state or intermediates, but we're not going to spend much time on activated. They're just very high energy things that we don't see. Now, there are certain factors that are going to affect the reaction rate, how fast something goes. How do we make a reaction go faster or slower? Well, basically, what the reaction is. I'm not going to lie to you. Alcohol and acetone, both of them burn. Acetone is more volatile. It burns a lot faster. Just by the nature of what it is, it's going to be more reactive. Oil will burn. Oil burns really slowly. Alcohol and acetones burn very rapidly. The other thing, concentration, having more of it. More stuff, more reaction. That's pretty straightforward, okay? Other things, having the particle size. So now if we want something to react, we want more surface area. So we could light a whole bottle of alcohol on fire, but that's going to burn kind of okay. Or we could pour it out on the table and light the table on fire like we've done before. That all works. How come we spread out the surface area? We made more molecules come in contact with each other. And then, of course, the other thing, temperature. By increasing the temperature about 10 Kelvin, we're going to double the reaction rate. So most of the time, as long as we're not, in some strange reactions, doubling the rate or doubling the temperature doubles the rate. 10 degrees doubles your rate. Sorry. How come? Because we're moving particles faster. More particles moving faster, more activation energy. So basically, make the particles smaller, increase the temperature, and then our last but not least, our catalysis. Excuse me. Come on. Next slide, please. Catalysis. Catalysts lower activation energy. So by lowering that hump in the activation energy, we're going to make things go faster. We could also have things that are called inhibitors. Inhibitors slow down reactions. Now, we don't want that to happen too often. We want that to happen sometimes in food reactions where things are cooking. We want to slow things down. So what do? Well, we bake our cookies at about 350. We don't bake our cookies at 500. Okay? The other thing is in nuclear reactions, we're going to want to control how fast that nuclear reaction goes. And so they set in these rods that are called control rods that sit in between the fuel rods, and they slow down the reaction. They're called inhibitors. We're going to talk more about catalysts in a few minutes when we get to the diagram, but basically, there are two types. There's homogeneous catalysts. These are catalysts that basically are in the same phase. These are enzymes. Enzymes are homogeneous catalysts. They're still the same state of matter. They're just there to make the activation energy lower, make things go faster. The other ones are called heterogeneous catalysts, and these are usually different states of matter. And the only one of these I can really think of for our purposes is a catalytic converter in your car. This is part of the exhaust system that converts your gases. And basically this is metals, palladium and platinum, that we send our exhaust gases over, and those exhaust gases are then turned into water and more safer nitrogen gas. And so we have those. Now back to our collision theory. Why does increasing the temperature increase the rate? Because if we increase the energy on the x-axis here, the number of particles that are going to have the sufficient collision energy goes up. And so what we want to do is try to raise the amount of particles that have this amount of energy, the activation energy. And so only those numbers in the green area here have enough to react. So what do? By increasing the energy, by heating it up, we're going to push that curve further to the right and get that portion of the activation energy a little bit larger. Now with this, we also have concentration. Concentration means you put more stuff in, it's going to react, plain and simple. Okay? More concentration, more collisions. Super simple. What else do we have? We have particle size. How come particle size affects things? Well, the smaller the particles, the more collisions there could possibly be. Big particles are going to collide, sure, but they're going to collide and they're going to bounce off. They're not going to have sufficient energy. They're not going to have the activation energy that we need. So we need smaller particles to make them go faster. And the way we do that is we grind things up. We cut up little pieces of solid. We use our mortar and pestle and we pulverize powders into smaller particle size. Okay? And what that does is that increases the surface area. So by taking this big piece and breaking it up into smaller pieces, now there's more surface area for the reaction to occur, right? Last thing on catalysts we have coming up, a little bit of revisit there, is these are substances that speed it up. And we already said how. They speed it up by lowering the activation energy. Here's what it looks like. If we start with reactants on the left, if we don't have a catalyst, we've got to go over the blue hump. That's a lot of energy. So what do? We add an enzyme or we add a catalyst, a heterogeneous one, and that's going to lower the activation energy. It's going to make things go faster. It's easier to get over a lower energy hill than a higher energy hill. Right? Here's what those catalysts may look like. We would write those over the arrow. Okay, so this MnO2 is going to speed up this reaction. This is a reaction that I did on Halloween for you guys called Genie in a Bottle. I took some hydrogen peroxide with some manganese dioxide and I took the cork off the bottle and the genie came out of the bottle, big plume of smoke. All right, and that went more quickly because I added the MnO2. Inhibitors, we've already talked about. These are molecules that interfere. They slow things down. Usually, they're interacting with the catalyst. They're getting in the way and they're slowing stuff down. Excuse me, I got ahead of myself. Okay, so that's catalysts and intros to rates. What makes things go faster? So when we think about it, we're talking about catalysts, we're talking about particle size, we're talking about temperature, and what we're trying to do is figure out how to make reactions go faster. Any way we can, we're going to make these reactions go quicker. I'm Smath. I've got another video coming up for you on how we calculate what's called a reaction rate.